Hello and welcome to another Reigate Maths video. In this video we're going to be focusing on the Algorithms on Graphs chapter from the first year of the Edexcel Decision 1 topic for further maths. My name's Simon and this video specifically is focusing on Dijkstra's algorithm, or the shortest path algorithm. First published by the highly influential mathematician and computer scientist Dijkstra, the algorithm finds the shortest path from one vertex, also known as the source vertex, to every other vertex in a weighted graph. For the Edexcel specification, the layout of this algorithm is incredibly specific. And the first thing you have to do is you have to start by relabeling every vertex in the network with a box that looks like this. The whole point of the algorithm is you label the vertices as you go. So in the vertex box here, we will write the name of the vertex, typically a letter. In this middle box, we will put the order that we choose the vertex in. In this large lower box, we're going to put weights of paths to get to that vertex, and then once we have found the shortest weight to that vertex, we will put in the final label there. So here is a description of the algorithm, again, as the way we are going to approach it for the Edexcel specification. So you will label the starting vertex, that source node, with a 0 for the final label. The final label is the distance from the starting vertex to the vertex you're talking about. So the shortest distance from the start vertex to itself is 0. So the working values is the main thing here. What you will do is you will write down the shortest distance from the vertex you are currently looking at to all vertices directly connected to it. The important thing is when you write things down. So if we're on vertex X and we are looking at vertex Y, the working value we write down is going to be the final label at X plus the weight of the arc that joins the two vertices together. If the working values table is blank, then you just write the number down. But if there are numbers already there, we need to check. If there is already a working value there, we only write it down, the new one down, if it is smaller than what's already there. If it's larger than or equal to a number that's already in the working values table, you do not write it down. You can write it down and cross it out, but it's better to just not write it down at all. Once a vertex has its final label, you don't revisit it. You just leave it there. And you just don't consider it anymore. Even if you would be going back on yourselves, you just don't do that. Once you have labeled a specific vertex, so once you have written something in the final label box for a vertex, you look at all of the working values in all of the vertices that don't have a final label. You pick the smallest one as the vertex you are next going to consider, and you keep repeating until the final vertex has a label. To find the shortest path, you trace backwards. If a vertex already lies on the route, you include an arc to it if the final label of B, the vertex you're looking at going backwards, minus the final label of A, the vertex you're looking to go to, is the same as the weight of the arc AB. If it's not, you don't choose that arc. Now that's quite a wordy, unpleasant description, so best thing to do is we're going to look at an example. So this is the example we're going to be looking at. Use Dijkstra's algorithm to find the shortest route from S to B. So the first thing first, we need to redraw the network using these boxes here. Quite often, that will be done for you, and you'll be given a grid in which to fill out. Okay, but it is also useful to know how to do it yourself. Okay, so this is vertex S, and we go to A. The neatness of these boxes is not hugely important as long as they're all in the right place. Here's C, and so on. Make sure all the arcs are connected appropriately, and I would advise labeling the arcs as well if they haven't been done already. So here is our network set up for doing Dijkstra's algorithm. So let's follow this through. So our first instruction is label the start vertex S with the final label 0. So remember, final label goes in there, and we have labelled S first. So we put a 1 in the middle box. There's no working values because we haven't done any working out. So we put a final label in S, and we've labelled it in the order that we chose it. So S we chose first, so we put a 1 there. What we're going to do is we look at all of the arcs that come out of S and write down the weight in their destination working spaces. So the weight of S to A is 7, that goes there. S to C is 5, and S to D is 4. So now we don't have any other arcs that come out of S to an unlabeled vertex. So now we look at the working values in all ones that don't have a label. The smallest is here at D, so that means we are choosing D second. We put the smallest value in the working box in the final label, and now we look at the arcs coming out of D. So we've got dt here, which is 7. 7 plus 4 is 11. So we put an 11 in the working value of the T box. D to C is 2, so the path SDC has a length of 6. 6 is bigger than 5, so we don't write the 6 down. We've now considered all of the arcs coming out of D, so we're done with D. Again, we now look at the smallest working value in the boxes that have them so far, and we can see that 5 at C is the smallest one. So we're choosing C third, and the working value there is 5. We repeat the process. 5 plus 7 is 12. That's bigger than the 7 already there. We don't write it down. 5 plus 6 is 11. We write that down there. And we're done because there's no more arcs coming out of C. A, we can see, has the next smallest working value. So A, we're choosing next. And there's only one arc out of A that we haven't already dealt with. So A to B is 8, which gives us a working value of 15. Repeating the process, we now have options. We can either choose E or T, and it actually doesn't matter. If it happens to matter, so if for whatever reason the weights here, if we added them, gave us a different order of working values at B, the mark scheme would account for that, but they generally don't do that. So this one, it doesn't actually matter. I'm going to choose E first. So E to T is 8, 8 plus 11 is 19, so we don't write that down. E is 11 plus B, so is 3, which gives us 14, so we write a 14 down. Leave a space here, so it doesn't look like 1514, but don't cross out the 15, leave it clear, like that. We now choose T. We can see T plus 9, so 11 plus 9 is 20, that's bigger than the 14 there, we don't write it down. And then B, There's nowhere for B to go. We fill it in, and we're finished. We found the shortest distance from S to B, but we need to work out the actual route, because that's what we've been asked to do. So we can see, working backwards, 14 minus 7, so B, so the working value, not the working value, the final label at B minus the final label at A is not equal to the length of AB. So AB is not on our path. We can see that BE is going to give us that path. So you could write it down, you could put an arrow on if you wanted, or we know that our final vertex is B, and we just write from right to left. This one, because it's a relatively small network, we can see very clearly and quite quickly that our shortest route is SCEB. But doing the check like we did here, so the final value at B minus the final value at A was 7, which is not equal to the length of AB. So AB is not on our route. For a larger network, that can be quite a useful check, because finding the route genuinely can be the hardest bit. Because with a large network that's got lots of arcs, it can be very easy to get lost. So this check is very, very useful. And that's Dijkstra's algorithm. Now, like I've said in previous videos for decision, we are focusing on the Edexcel method. This layout could be incredibly different for other exam boards. The process is the same, but the layout is very, very different. So you do have to be careful about that. This is the Edexcel method. Now, this algorithm can be a question just on its own, but quite commonly what they will do is link this with the route inspection problem, which we're going to cover in a later video. Because that algorithm relies on you finding the shortest distance between several pairs of vertices, which Dijkstra's algorithm does to some extent. But that's it for Dijkstra's algorithm. Thank you for watching.